So, so in today's lecture, I'm going to cover the elasticity equations again. Um, we'll be covering the elasticity equations, and we'll be discussing how these equations can be used to analyze pressure vessels. So, one of the areas of my expertise is aircraft and launch vehicle designs, for example. Um, and a lot of these designs involve thin wall structures that have cutout windows and things of that nature. So in this course, we're going to help, we're going to use some of these equations to learn how to analyze those cases. But before I go into those cases, I want to teach you some more fundamentals and how they apply to pressure vessels, because that's used quite a bit in design. Now, you may ask me, well, if I have a finite element software that can analyze every condition that I have, that I may encounter in design, why do I need to learn any of these equations? The answer is, in real life, you cannot model every single little feature of a design in a finite element software. And the reason is because you may have design features that are too small. For example, an aircraft that's extremely long and has a lot of surface area, it will be very challenging to simulate every single rivet hole in the aircraft, right? But instead, if I can use that model to inform the far field stresses, I can then take that information and analyze those features using closed form solutions. In our industry, we don't memorize equations, which is the reason that I'm not going to ask you to memorize equations. What I want you to do is learn the concepts so that when you step into real life, you know what these concepts mean. You can open the book and figure out what equation to use. But in reality, you don't want to memorize equations. There's only few equations you want to memorize, and I'll show you which ones could be useful. Even those, you can probably Google them. So, all right, so today we'll step into that. And so we covered already that there's elasticity equations that are used in design. These elasticity equations are being solved by the finite element software. So you're not doing that by hand, but we are doing it by hand so you can learn how these things work. So we taught you in lecture 0 through 3 or so that the three governing equations are given by the ones you see here. These are the three governing equations. These three governing equations were derived using Newton's law. Summation forces equals ma, but we use the integral form of Newton's law to figure that out. These equations here that we're showing here have the stress states. And what is a stress state? A stress inside the body of the material, maybe within the fuselage or within the wing. That stress state are the internal forces really that are reacting to external loads applied to the aircraft. So why do I need to know that? Because that is the way how you design systems. That's how you predict failure of a system. Where the stresses are the highest is where the problem areas could be. And so if I have very high stress in an area and I predict it's going to fail, perhaps what I want to do is increase the thickness in that zone so I can decrease that stress there. So that's sort of what we're trying to achieve here. And then the other thing that we see here is the body forces. So body forces can be like gravity and things like that. And then we cover the 6 strain deflection relationships. And we also learned that the 6 strain deflection relationships relate the 3 components of displacements to 6 components of strain. And 3 of those strains cause a cube to stretch or contract, but also the other 3 components of strain, the shear strains, those shear strains cause the cube to distort. So as you can see, so far, we have 15 unknowns, 6 stresses, 6 strains, and 3 deflections. So the way to really complete the set of equations is to add 6 more. And the way you do that is to go to the labs to do experiments so you can relate the stress to strain. And the stress is related to strain through the modulus of elasticity, the Poisson ratio, and these are things you can measure in a lab environment using a machine. And so we've already covered all that stuff. This is more like a summary. And so these 15 equations, 15 unknowns will be impossible to solve by hand for an aircraft, say, with loads applied, or a launch vehicle design, which has bending loads applied and pressure applied and all kinds of loads applied. So very, very hard to do. But it is worth understanding how these equations are used in some closed form solution examples, so you can have a better understanding on how this works. So these quantities are within the body of the material. They're not on the surface of the material. Another thing to point out, the stress states are symmetric. So for example, the shear stresses are symmetric. And the reason for that is because of the moment equilibrium. We cover that also. So now we go to the boundary condition. And what is a boundary condition, right? So a boundary is something that encloses the body of material of interest. So an aircraft is the body of material of interest. But what is the boundary of the aircraft? It's the surfaces that enclose the body of material of interest. Any surfaces that are exposed to the air, for example, those are the body, that's the boundary, right? And that is the only places you can apply loads. For example, a wing is going to experience loadings on the wings from lift and drag, for example. That's going to be acting on the surface of the material. You can't really apply a load inside of the body of the material, but you can apply loads to the surface of the material. The door in this classroom, for example, when you open it, if you want to figure out where it fails, you look at the inside of that material, the wood, but you apply loads on the surface by pushing that door out. So you're applying that pressure load. So very similarly, you can see here in this picture, a body of material, and here you can see tractions applied on the surface. Those tractions can take any orientation. You can have tangential or pressure applied on that surface, or you can have a fixed boundary condition. You can actually hold it on the surface, right? And then you can take these tractions, the loads that you applied, you can relate them to stresses just inside of the material. And we use Cauchy's relationship to figure that out. So we learned that tractions are equal to the stress state just inside the body of the material times the normal to that surface. Is that correct? We kind of went through that. Okay, so we'll continue here then. And this is more like a map to show you all the things that go into a simulation. You have external loads, you have internal loads that are really your stresses there. They're reacting to external loads applied. And the stresses are going to help you figure out where the structure is going to fail. So that's the idea there. Stresses are related to strain through the constitutive law, and strains are related to displacement through the kinematic deflections. So when you're solving problems, you're going to be using all these equations as a whole to be able to tackle certain problems. So the stress equilibrium equations I showed here, these three equations I showed you here are valid for in a Cartesian coordinate system and 3D. But we can actually write the equilibrium equations differently in polar coordinates. And I covered that in a previous lecture. This is very useful because if you can write it in this manner, you can then solve it for problems where you may have like a cylinder or some axisymmetry, or a situation where like a sphere, for example. This polar coordinate system is very helpful because you can solve problems in that domain. Here, Fr is a body force in the radial direction. F theta is the body force in the tangential direction of the cylinder, for example. Sigma RR is the stress along the radial direction of that cylinder. Sigma theta theta is a stress tangential to the cylinder, so it's tangent to the cylinder, while sigma r theta is the angle change between the r coordinate and the theta coordinate. So if I look at the strain deflection relationships in polar coordinate systems, which we also discussed, they're shown here, and they can be derived from the Cartesian system fairly straightforward. We won't do that here because it's discussed in the book, but these are the equations that will work for polar coordinate systems. you'll notice very clearly here that I'm not including other terms. So I'm not including the ZZ direction. So if you have a cylinder, there's a Z direction through the thickness. That direction, I'm going to consider that these problems are plane stress, for example, where sigma ZZ is close to zero. So we can ignore the other components of stress. And as a consequence, we're simplifying the problem to the ones you see here. And that's okay for what we're trying to achieve today. Okay. So what are the unknowns here? I want to make sure we have a clear understanding of the unknowns. So you have three components of stress that are unknown: the radial stress, the shear stress, and the stress along the theta direction, the tangent direction to that cylinder. Then you have the three components of strains are also unknown. And then you have three deflections are unknown. And when I look at, or sorry, I have two deflections are unknown, as you can see here, the radial deflection and the tangential deflection of a point in a cylinder. So what you see here is you have 8 total unknowns, but yet I have 1, 2, 3, 4, 5 equations. I'm missing 3. And the other 3 equations come from the constitutive law. Proceed here. We'll proceed now with a thick cylinder, pressurized open cylinder. I'll be covering cylinders today that are pressurized. Very, very helpful for the design of pressure vessels that are used here in mechanical applications like power plants, aircraft, launch vehicles, and spacecraft and aircraft applications. And submarines as well. You can actually use this equation to design submarines. So here, what we're discussing then is I'm applying an external load P naught, an external pressure P naught. Internally, I'm applying a pressure PI. And then the inner radii of this annulus is A, and then the outer radii of this cylinder is B. So it's a very thick cylinder. In a lot of applications, it's actually thin, but there are applications where it's fairly thick. So if I assume that the deformation of this body of material is axisymmetric, meaning I don't expect this point here to move tangentially. I expect that every point around the circumference is going to move radially together, then no point here is going to move tangentially. Then that is called an axisymmetric problem, where the deformation is independent of theta. So that's what we have here in this case, the one I want to study today. And so this term goes away because the partial is with respect to theta. There's no radial body forces. I'm not applying any body force that could cause this to grow radially. Later on, we'll see examples like that. Here, the partial with respect to theta also goes away as a consequence. It's not always the case, is that for this case, it makes sense, right? If I apply pressure to a body of material that's cylindrical, a shell, then I expect every point of that shell to move radially out about the same amount. I don't expect any theta deflection, any torsion or anything like that. So that's why this makes a lot of sense to me. F theta also is 0 because I'm not applying some spinning load where it could cause a body force in that direction. So we don't have that term. So under pressure, we also know that there's no tangential deflection. We know that for sure. So the strain deflection relationship really boils down to what you see here. The radial strain is a partial UR respect to partial R, where the R is a radial direction we're talking about of that cylinder. UR is a radial deflection along the R direction. Epsilon theta theta is going to have this term right here that goes to 0. And then you have UR divided by R. That's epsilon theta theta there. So you're going to have, you can think about this. If I take a pressure vessel, a cylinder, and I expand that cylinder, you can imagine that there's a strain in the circumferential direction that's kind of reacting that thing wanting to expand radially out, you know. So think about that carefully more. So if I have a cylinder and the cylinder shell wants to expand out, then this band around, put like a rubber band, put a rubber band around a cylindrical shell in your head. You know, close your eyes and think about that. You put a rubber band around that circumference of that cylinder. I apply pressure, and now what's going to happen to that pressure vessel? It's going to expand radially out, right? Correct? Are you guys here? And what happens to that rubber band then? It's changed length, right? It expanded. So that it is the strain that we're talking about. That is the epsilon theta theta, physically speaking about it. The partial with respect to theta is 0. U sub theta is 0 because we don't have any deflections circumferentially. And so there's no shear strain. You can see that there. And if there's no shear strain, because the shear stress is equal to the shear modulus times the shear strain, then there's also no shear stress. And the third equation just completely goes away. It doesn't even come into the picture. So the only equation that really matters then, so in essence, we have this term also goes to 0 right there, because we know that sigma r theta equals G times twice epsilon r theta. But I found that all these terms go to 0, which means that this goes to 0. So that goes to 0. And so now I'm left with this equation alone. So things got simplified quite a bit. Now I'm going to assume that the cylinder, I mean, it's almost impossible to have the situation that I can think about. But think of a cylinder that's pressurized but has no end caps. It's unconstrained. Therefore, the stress in the axial direction should be 0 because I'm not applying any load in that direction. So say if I have a cylinder that looks like this, and I apply pressure here, this direction Z has no load because all the pressure I'm applying is circumferentially. That's the pressure that I'm applying. I'm applying it here, 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 around the circumference, right? So there's no load applied axially in this case. It's unconstrained. It can grow in that direction. Then I can use Hooke's law again. You guys already know Hooke's law because I taught you how to use Hooke's law for assuming plane stress. And you can see here that I get this equation here. You can see that equation there. So that's this equation here, sigma RR, and then you have sigma theta theta. This is how you relate stress to strain. And we already know how to create that relationship. How do I establish that relationship? I establish that relationship using I go to the labs and I do testing to get modulus and Poisson ratio. That's how I do that. Okay. And I know epsilon R, I know epsilon theta, right? So I know those two in terms of deflections. I had that in the previous slide, if you recall. So if I go here to this slide, you can see that I know epsilon in terms of deflections, and I can plug that in here. It's plug and play. I put that in there, put that in there, and now sigma RR is only in terms of deflections. You can see that here. Sigma theta is also in terms of deflections. So the only thing now left is to take sigma RR and sigma theta theta right here and plug it into this equation here. And if I do that, I get this differential equation. And that differential equation is only in terms of U, the deflection U, which is great because now I can use differential equations to solve that for you by integrating that or assuming a solution e to the x. And if you assume e to the x, it turns out that you can actually solve this problem fairly straightforward. The question on the line here in person, the question is why FR is 0? Because there's pressure applied. And so your question is why is FR not the pressure? So let's think back again. And I want to make sure that concept is clear because that's a very good question. You can see that pressure can only be applied on the surface of the material. You see that, right? The pressure can only be applied on the surface of the material. While this body force is acting at every point within the body of material. So this Bx, By, Bz is intended to represent a gravity, like things that act on every single point of the body of material. Let me give the example of a bicycle. You have a tire, right? The tire, the faster you go, you agree that that wheel is rotating very fast. Well, that's going to cause a centrifugal force, right? So that's going to cause every particle to want to go outwards, as an example, right? Every point wants to go outwards because of this. You're spinning that disc or spinning that wheel. That'll be a body force because that's acting every point of the body. But pressure in the case of the bicycle, the wheel, is the wheel touching the ground because the ground can only touch the surfaces. So again, you can only apply loads on the surface, or you can apply them to every point of the body if it's a body force. And pressure is not a body force. Does that make sense? So here you can see that me putting pressure for FR doesn't make a lot of sense because pressure is a traction force and it's not a body force. Okay, great. So great question. I love that question. That's a great question. So now I got to this differential equation, and now all I have to do now is to solve that differential equation. And when I do that, because I'm not going to ask you to do it because you already learned how to do it in a different course. You can also open up wolframalpha.com, enter the equation, and it will solve it for you. Or maybe you can use now, they have this AI stuff where you tell it, hey, chat IGBT or whatever that's called. Can you tell me how to solve this equation? And then it solves. I don't know if it does it. Maybe somebody can tell me later. And then you can tell it to if it doesn't give you an answer, you can say it to go away, right? But here it is, a differential equation of second order, which is going to have two constants of integration that needs to be solved for. So now I plug that solution. I'm going to plug this solution here of this differential equation. And let me make sure we're all in synchrony again, because I want to make sure that question that I asked doesn't get everybody confused. But there's two equilibrium equations, three strain relationships, and you can see here, all we were trying to do is to get stresses in terms of deflections, plug that into this equation here at the top, which is, I repeated here at the bottom, to get it all in terms of U. That's a strategy. I got it all in terms of U. Now I can solve for it. And once I solve for it, that deflection U is a deflection going radially. That's what that is. So I can take that deflection and plug it back into the constitutive law. So for example, I can plug this C1R plus C2 divided by R. I don't know C1 and C2 yet, but I can plug that in there into this equation sigma R. And when I do that, I get this one here at the bottom. Now, how can I use that? Well, you asked me the question. You asked me, how can I use attractions? Because have I introduced pressure yet to the problem? I haven't, but I will now because I know something. I know that sigma RR, isn't sigma RR the stress that's radial, right? So the sigma RR is going to take a value of pressure at the surface. It has to be, because sigma RR, remember Cauchy's relationship where traction equals sigma times the normal? Well, sigma RR and the normal to the surface are perfectly aligned. So the tractions are aligned with stress, sigma RR. So you can see that there. Let me draw it for you so you can kind of see it visually, right? So I'll draw it in blue. So if sigma RR is going outwards like that, right? Then the traction load I'm applying, so let's look at R equals B, like the outer surface. So in the outer surface, sigma RR is the traction is applied in the opposite direction. You can see that, right? That pressure. So sigma RR is equal to the minus P naught. It has to be because it's reacting in the opposite direction. Now I can look at sigma RR at R equals A. At R equals A is just inside that surface, just inside, just right here, right? But sigma RR is going to be then at R equals A minus the pressure just inside the surface. So you can see now how the pressure came into the equation. It came through the boundary conditions. So any loads you apply to the system are always going to come and or they're going to always be introduced through the boundary conditions. And you can see that happening here. So guess what? I have this equation sigma RR that I have, and I know that sigma RR is this equation in terms of C1 and C2, but I know that sigma RR is a pressure of PI right at this point, this surface, R equals A, the radius of R equals A. And I know that sigma R at the radius of R equals B is the pressure outside that's been applied. So now I have two equations and two unknowns. I have C1 and C2, C1 and C2 for the second equation. And now again, I can use Wolfram alpha or some code to solve for C1 and C2 because it's a linear system of equations. I can solve for C1 in the first equation, plug it back into the second equation, and then solve for C2. And once I have C2, I have C1. And as a consequence, I know the stress. Sigma RR right at the surface. So the unknown coefficients can be easily found as C1 to be like that and C2 to be like that. And so now I can find the hoop and radial stresses fairly quickly then, because why? Why can I do that? Let me show you how. So do you agree that sigma RR is this equation here? Well, I already found you, so all I have to do is plug it in here, right? And then I can have sigma RR in terms of u. And because I found you already, I get this equation. Sigma RR equals this, the radial stress, and the tangential stress is this one. And the deflection that you get is this one. It looks very messy, but let's break this down. It's not that hard, right? So let's look at the deflection. Or let's look at the stress, for example, the radial stress. The radial stress is a stress acting along the radial direction. So that stress right there is equal. And let's look at the unknowns here. What are the unknowns? The knowns. What are the knowns? You know the inner radii is A. I know what A is for a given problem, right? You know B, which is the outer diameter, the outer radius. So if I go back to the plot here, B goes from the center all the way out. So you know B will be known for any given problem. You know the pressure inside of the cylinder, and you know the pressure outside of the cylinder. So all of this is known. It's actually a single number. Minus, and then you see an R squared here in the denominator. I don't know R, but I can vary R. So I can actually plot sigma R versus R because I know A, B, Pi, and P naught. So in this equation, sigma R varies relative to R. That's what it does. So it's varying relative to R. You can quickly see, or maybe it's not that quick, but you can probably check that if you put R equals A here, so if you put R equals A right there, that you recover exactly the boundary condition here, the Pi. And if you plug in R equals B, you will recover P naught. Is that making sense to you guys? Is it connecting? Then when you look at the deflection though, you get the Poisson ratio involved and you get the modulus involved. Okay. But everything else is known. And the only thing that's not known is R, but R is the one that you want to plot that radial deflection versus R so you can see how the cylinder expands, right? You can plot that now. Okay. With that, okay, so we'll continue here. That was an excellent question. We'll continue here. Now, if you wonder how that cylinder grows, right? Because when you expand that cylinder, due to the pressure applied, due to the Poisson effect, you expect the cylinder to grow also cylindrically, sorry, axially. So this is what I expect. I expect this. I expect that if I apply pressure to this vessel, P naught, I expect the cylinder to either grow that way or contract that way. But in this case, it's going to contract. And I'll let you check that at home. It makes sense. I'm expanding the cylinder, but the volume has to be somewhat preserved. So then the cylinder is going to contract. So that's what is going on there. And I hope that's clear to you there. And so I can use the plane stress equation to figure out what epsilon ZZ is. I know sigma R and sigma theta from the previous equation here. I know sigma R and sigma theta. And because I know these two, all I have to do is plug it in here, and then I get epsilon ZZ as you see here. So that's how you find the stress in that direction. So not the stress, I'm sorry, the strain, how much it grows in that direction. Okay, so now I'll move to thick cylinders, but they're closed. So the pressure now is applied, but now the cylinder is closed. So now that pressure reacts against the end caps. Okay, so let's look at the case of the closed cylinder. In a closed cylinder, what you really have now is like a cone of, like a can, Coke can, right? Or Sprite, whatever you prefer. I'll say Pepsi just to cover everybody. But if you have a cylinder that's pressurized, it's going to react against this wall. You agree? Right? But if you have pressure outside also, then you're going to have pressure in these caps too. And so the thing you can do then is to look at the pressure here, right? That pressure there. And then you have this pressure here. So what I can do then is look at how that's reacted by the force here as well. So let's look at this together, right? So if I sum forces, and I did it already, but I want to do it by hand. So sum of forces in the x direction, let's say. Actually, let's in the x direction where x goes this way, say, for example. Okay, just let's do it this way. So what is the force due to P naught? So the force due to P naught is definitely going to the right. So that's P naught times pi. And then what is that length there? That's going to be B, the radius squared. But then you have this pressure here, Pi, which is acting in the opposite direction. So that's Pi, that's a force now. Pi times the area is the force. So P times the area squared. But this right here is A, 2A, I should say. That's 2A, okay. And so the force due to the P naught is this one here. The force due to Pi is this one here. But then I have this force here. That's if I do a cut, like a free body diagram. If you recall back in the day when you do free body diagrams, there'll be a force there, right? Also, correct? There's also a force there, and I want to figure what that stress developing there is. So let's call it for now. Let's call it SCZ for now. So that's also acting in that direction. So SCZ times. And what is the area of the annular ring? The area of the annular ring is pi. And then it's going to be B squared minus A squared equals 0. So that's what I did. And I'll show you in a second. So I'm going to go ahead and erase the marks and show you what I got when I did it. So I got this, which is what I showed you, but I did it little by little so you can kind of follow me. So this right here is due to these forces. This one right here is due to the stress acting in this cut. The beautiful thing about this, I can solve for sigma z, and I did it there. You can see I solve for sigma z, and I get the stress in the axial direction due to a pressure applied inside and outside, but now the caps are closed up, which is a slightly different problem. Looking at more cases then, let's look at a thin cylinder now. So you saw the equation for thick cylinder, but it turns out that for thin means that the thickness to radius ratio, that ratio is fairly small. That's what that's saying, okay? So it turns out that for that case alone, the formula simplified quite a bit, and it's worth memorizing those because I've used them all the time for design. So we're gonna assume no external pressure. I've been applying external pressure all along, but for now I'm gonna say that P naught is not there, so I'm gonna kind of ignore P naught. But the term I want to really examine with you carefully for a thin cylinder, I want to examine this term right here. That term, because that term is showing up everywhere, showing up there, here, here, here. So let's look at that term carefully. B squared minus A squared. If you go back to algebra, so you can see here that, so say the radius is R, the mean radius is R, say, or the radius, okay, so sorry. Let me backtrack a little bit. Let's say the radius, inner radius is R, and the thickness here is T. So then B becomes R plus T, correct? So what I did there is I plugged in what B is in terms of R, the radius, the inner radius, plus T, and then A is just R, the inner radius. Remember, B was the outer radius and A was the inner radius. The outer radius is the inner radius plus the thickness. I'm just changing variables to make it easy to follow. What I can do this calculation and factor 2RT, and when I do that, I get 2RT times 1 plus T over R. It turns out that let me give you an example. If the thickness of a fuselage, the thickness of an actual airplane, okay, let's choose that as an example. The thickness of that fuselage, that wall, when you step into the airplane, I ask you to do this because it's fun. You step into the airplane, don't look suspicious, that's not good. Go into the airplane and then touch the fuselage thickness. It's going to look like this thin, very thin, in the order of 0.15 inch, very, very thin. But and you wonder how that thing flies, right? We'll talk about that. R is very big, is in order of feet. Do you agree that T over R is basically 0 in that case? So that pretty much goes away. And you can say that B squared minus A squared is pretty much 2 times RT, because 1 plus 0 is 1. So 2RT times 1 is 2RT. So right there, you can simplify now some of these equations, and I'll walk you through each of the simplifications. So let's look at this. Anywhere I saw B squared minus A squared, I plugged in 2RT. So you can see here, I plugged 2RT. Everywhere I saw that. So anywhere I saw B squared minus A squared, I just plugged in 2RT. Another thing I did is, listen, if I have this situation, I told you already, B equals what? R plus T, correct? I can factor R. Don't I get 1 plus T over R? Right? If T divided by R is very small, isn't this approximately equal to R then? But A is R. So A is R, and B is approximately equal to R. So anywhere I saw A or B, I plugged in R because it doesn't matter if it's very thin. Okay, is that clear? The next thing I did is to realize that I have an R there still. But you can see that R has to be between A and B, right? But if A is R and B is approximately equal to R, isn't that mean that the radial coordinate is basically R? So anywhere where I saw R, also I plugged in R. And when you do that, you get the sigma radial, the stress in the radial direction is 0. You get the hoop stress, which is the stress going this way in the hoop direction. That stress, sigma theta theta, is the pressure inside the vessel times R divided by T. And it turns out that the stress in the axial direction, when you do a simplification as discussed, is going to be the pressure inside the vessel times the radius divided by 2T. And this equation here, this is the axial stress. So that stress is going this way. Let me show you which way. That's this stress, sigma ZZ. That's the axial stress. And you can see it's half of the hoop stress. It's exactly half of hoop stress. And that's, I don't know about you, but I think if it's a thin cylinder, these are easy to memorize. while the ones for thick cylinder, they're way harder to memorize. So that's why it's a good idea to memorize these ones because they will come up in design. So this sigma z here is showing up because the ends are closed. So if you apply pressure, do you agree with me that if you apply pressure to a can of Coke, you expect it to expand also, and there'll be a stress associated with that? That's why. But if that end cap was not there, those caps were not there, then you don't expect any stress in that direction. You only expect it to grow or contract, right? So that is what's going on there. These are formulas that are very good to memorize. I invite you to do so. I've done it myself, and I think it's a good idea. There's another way to derive that equation in a simpler way, and I did it here for your own edification. We can do it fairly quick if you like. It's not that hard. So let's just do it together. So if this radius is r, say, right? That radius r. Okay. And the width of this thing was, say, the width of that thing, that little ring that chose, let me call it h. I use dy here, but just call it h for now. The area of those little pieces, the area of this piece and the area of this piece is going to be how much? It's going to be h, the thickness times h times thickness twice. Okay, that's the area of those little squares. And then I have a stress associated with that, sigma 1 acting on those little rectangles. Right, you can see the sigma 1 right there. That's acting on these little squares there. Then I have that pressure acting on this projected area here. That projected area is minus P times what? It's a rectangle too. It's 2 times R. And the width of this thing is H. That has to be equal to 0. So when you solve for sigma 1, you actually get the same equation I derived earlier. The very same equation. So the hoop stress can be derived in a very simple way, like I showed there. Okay, so now let's examine this one here, the axial stress. So if I look at that surface, this surface, I look at this looking that way, right? Those are scary eyes, but okay, so this is the one I want to look at. I look at a ring. I basically look at a ring that's very thin, but I'm exaggerating the thickness on purpose. This thickness is T, correct? And the perimeter of that is 2 pi r. This stress sigma 2 is acting on that area, this area. The area is approximately equal to 2 pi RT. So sigma 2 to 2 times 2 pi RT. And that's reacting a pressure acting on these end caps. So there's a pressure acting on this end cap here, over here, in the opposite direction. And that pressure is P times the area of the end cap, which is pi r squared. So now I can solve for sigma 2, which is a stress in the axial direction. And I get exactly what I showed you in the previous slide, but in a much, much simpler way. Okay. For a sphere, the equations are going to be very simple. Using a very similar approach that I just did, you actually find out that the pressure is acting on that projected area, and that projected area is pi r squared. Doesn't matter how you slice the cake or the sphere or the ball. And so therefore what you find is that the hoop stress, doesn't matter what direction you're looking at it, is going to be PR over 2T. So the stress, if I take any square, any cut is going to have a stress that's PR over 2T, which is not the case for cylinder. The cylinder is PR over T and PR over 2T. So that's what you get there for thin wall sphere. So any questions so far? So I'll be covering shrink fit as another example of this. So let's look at that. What is this problem about? What is this problem about? What is going on here? So this is a problem where you're looking at a outer cylinder and an inner cylinder. So we call this a compound cylinder. And this is something that's encountered in real life quite a bit, which is a good reason to learn this. What ends up happening is that this inner cylinder wants to push against the outer cylinder because you're trying to shrink fit it into the outer cylinder. And that's going to cause a pressure between these two cylinders. And this is a common problem that's analyzed. And I will give you examples later on how that works. So say that you have a system with multiple stress disks that can resist large pressures. Usually a system that can resist large pressures better than a single cylinder is looking at multiple cylinders stacked in the way you see it here. So let's assume that the external radius of the inner cylinder is larger. So this inner cylinder has a radius that's larger when it's not deformed at all. So it's kind of sitting there, no problem. But that cylinder, the external radius of the inner cylinder is going to be larger than the internal radius of the outer cylinder. So basically it's bigger than the external cylinder. And so you have to fit it in there to create a tight fit. And the amount that the inner cylinder is greater by than the outer cylinder is an amount delta. So the quantity delta is called the shrinking allowance, also known as a radial interference, but very helpful. One way you can achieve bringing these two pieces together is making one of the components hotter so it expands, and then you can bring the other one in and then cool both down and they'll come together tight. That's one approach. You can take the inner cylinder and contract it with applying cold temperatures, and you can bring the inner cylinder in and bring it into the outer cylinder. So two approaches, but you can see how the inner cylinder and outer cylinder, right, are going to be applying pressure to each other, right? But there is an amount delta that if it's too much, it can cause failure of one of these rings. And so the point here is how you analyze that. So then what you really have then is that the radial deflection at R equals B. So R equals B is from here to this point here, okay? From this point here, from this point to this point. And the inner radii is from R is a deflection up to this point. For the outer cylinder and for the inner cylinder, they have to be compatible right there at R equals B. There's no other way. So, but because they're different in the unstressed state, that's what the shrinking allowance is this delta here. Okay, so there will be an interference, a radial interference, and it's by this amount. Okay, so that's what is going on here. So now you can think about this. The internal cylinder is exerting a pressure on the outer cylinder. And I want to know what the pressure is, because if I know what the pressure is, I can calculate what the stresses are in each of the rings. So I'll just start with the equation I had before. Okay, this equation here, the deflection U, is the same one I had. I changed it a little bit. So if you recall, before I had A and B, right? A and B. But it was the same equation I had before. Remember the equation where I had a single cylinder with pressure applied outside, but also inside? Well, I'm going to use the same formula for deflection. The only difference is I made A equals, sorry. I made A Ri, I made that A, and R naught, I made it B, because I don't want to get it confused for what's gonna come soon. So that's why the equation looks different, but nothing dramatic has occurred yet. So I'm just using the equation we learned earlier, which was meant for cylinder. We have pressure applied outside of P naught and a pressure applied inside of Pi. So I'm just using that equation. Okay. So in our example, Pi equals P. That's the contact pressure. And if I look at the outer cylinder, let's focus on the outer cylinder. So I'm going to focus in this outer cylinder here, right? The outer cylinder, that pressure here that I'm trying to find is the internal pressure P. But for that same outer cylinder, the external pressure is 0. There's no external pressure. So what I'm going to do is take that, and I'm gonna make P naught 0 and Pi, the contact pressure P that I'm trying to find. So I'm gonna plug it in. And then for the radius, let's look at the radius of the outer cylinder. The radius of the outer cylinder is the inner radii goes to B, so Ri is B, and then the outer radii of the outer cylinder is C. So all I'm going to do then is just plug it in, and that's what I did. Plugged it in. So this goes away. A lot of these terms is a simple substitution, and I get this equation here. The radial deflection at R equals B is this much. So that's what I've done so far. Can we agree together? Can we agree together that everything here is fairly straightforward? Look, so B is known. I know the inner radii of the outer cylinder. I know C. I don't know the pressure P. That's what I'm trying to find. E is the modulus of the outer cylinder, because the two cylinders can be different of each other. They don't have to be the same. C, I know the Poisson ratio. So I know everything except for P. And that's what I'm trying to find. I can repeat the process for the inner cylinder. So I pretty much, I'll tell you how I constructed this PowerPoint. I copied this slide over to the next slide. And now you can see everything got changed to inner cylinder. And I use EI for modulus of the inner cylinder, Poisson ratio of the inner cylinder. So pretty much I changed everything. The only thing that changes now is the following. Let's focus on the inner cylinder. The inner cylinder, when I look at it, the pressure, the contact pressure is really an external pressure. So that error is a mistake because I copied it from the previous slide. But really, this should be P. And I said it here correctly. P naught equals P. So this error should go where it says PI, because there's no internal pressure there. You can see that, right? So that's 0, but the P naught stays, and it's going to be equal to P. So that's an error. So I corrected the pressure that's getting canceled. You can see that there. But everything else can be substituted. So the outside pressure is P. I know the internal pressure to the inner cylinder is 0. There's no internal pressure there in that cylinder. So that's 0. That's 0. I pretty much have everything now. So, and then okay, let's look at the radii now. So the inner radius of the inner cylinder is A. So that's Ri is A. The outer radius of the inner cylinder is B. So I'll have to just plug all that in, and I get this equation. Fairly simple so far. No complications. Now what I'll do is combine. So I know that the radial outer deflection at R equals B and radial inner deflection at R equals B added together should give me the shrinkage allowable or allowance. So I just added these two equations, and that's how you do this problem, because the shrinkage allowance is known. This delta is known, right? Right? So in this equation, let's look at what we don't know. So in this equation, the only thing I don't know is P. I know modulus of each of the materials. I know Poisson ratio of each of the materials. I know the geometry, all these A, B, C. I know all that geometry of those two cylinders. I know the shrinkage allowance. So if I know all that stuff, I can calculate P the pressure. And once I know P the pressure, I can go back and calculate stresses using the equations that I had discussed earlier. You can use the same equations, no problem. The stress field for internal and external pressure, you can just use the same equations. And once you know the pressure P. So very simple approach and very, 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 very straightforward there. Okay.